Hello, welcome to this lecture series on semiconductor materials. In the last lecture, I discussed about some important classifications of semiconductors, that is elemental and compound semiconductor. Then we also discussed about direct bandgap semiconductor and indirect bandgap semiconductor, and I also mentioned one important point that in the case of direct bandgap semiconductor, okay, when transition takes place from conduction band to valence band, okay, the energy is released predominantly as photons, or energy is um, the excess energy or the energy is released as photons predominantly. But in the case of indirect bandgap semiconductors, the energy is released predominantly in the form of heat when transition takes place from valence conduction band to valence band. Okay, now today what I'm going to do, I'm going to calculate the carrier concentrations, right, in the case of intrinsic semiconductor. But before going to start that, let me give some information on compound semiconductors. So as I told you, in compound semiconductor we have binary, ternary, quaternary and other mixtures also there. Okay, in binary semiconductors, right, I have told you we have we have 3-5 semiconductor and we have 2-6 semiconductors, right. We have other types also, but these are the two basic types of binary compound semiconductors. So in 3-5 we had discussed that we have gallium arsenide, okay, indium phosphide, then gallium nitride, then indium nitride, gallium antimonide, indium antimonide, etc. Okay, these are all examples for 3-5 compound semiconductors. But what is the advantage of 3-5 compound semiconductors? The advantages are, in 3-5 compound semiconductors, both n-type doping and p-type doping are possible. Okay, let me just write here. Both n-type and p-type doping are possible. Okay, which is very required one for making device. Okay, so this is very important. That's why in most of the modern days semiconductors or devices, you can see semiconductors based on these type of materials, 3-5 semiconductors. Okay, because both n-type and p-type are possible here. Then second one, here you can make these materials can be coated, right, as a single layer of single crystal. Okay, or I can say the other way, epitaxial growth is possible. Epitaxial growth is possible. You can make a single crystal, okay, as thin layer over a material, right. This is very important. Then third point, mobility is high. In the case of 3-5 semiconductors, mobility of the carriers, right, mobility is very high. Mobility is high. Okay, these are all some essential points that one should keep in mind, that the advantages of 3-5 semiconductors. Whereas if you go to 2-6 semiconductor, we have in 2-6 semiconductor we have plenty of examples, zinc oxide, zinc sulfide, okay, then zinc cadmium selenide, cadmium telluride, okay, cadmium sulfide, etc., etc. Many examples are there. Here, except cadmium telluride, except this, except cadmium telluride, in all other materials, okay, in all other 2,6 compound semiconductors, right, both type of doping, n-type doping and p-type doping are not possible. Okay, you can make either n-type doping or p-type doping, usually n-type doping, right? See, in zinc oxide, in zinc sulfide, these are all materials in which only n-type doping is possible, p-type doping is not possible, right? So this is a very important point that one should keep in mind, because while making device, okay, usually we prefer, right, for optical purpose, we prefer materials in which both n-type and p-type doping should be possible. Okay, so here zinc oxide, zinc sulfide, right, these are all material, they show only n-type doping, right? Only n-type doping is possible, p-type doping is not possible here. Similarly, if you take zinc selenide, right, many examples are there. In zinc telluride, I think this is the only compound in which p-type doping is possible. Okay, whereas in cadmium telluride, both n-type and p-type is possible. So except cadmium telluride, in all other 2,6 compound semiconductors, right, either n-type doping is possible or p-type doping is not both. So that's why 2,6 semiconductors, these material 2,6 compound semiconductors are not much used in device purpose, but it doesn't mean that they are not useful at all. No, they are also very useful in other applications. Okay, yeah, so keep this point in mind, this is very, very important, right? Then about ternary compound and quaternary compound, I have already discussed in the last class, right? And we can also, by making the composition, I think I have told you, for ternary compound, let me take one example. Algas, aluminium gallium arsenide. Okay, algas is a ternary compound. In algas, as we change the composition of the x, okay, as we change the value of x, that is actually if we change the composition of aluminium, right, what will happen? The band gap of the material changes. So you can alter the band gap, right, according to our need, right? So this is a very important one in the case of ternary compound semiconductors. We also have quaternary compound semiconductors and other semiconductors, right? Okay, so with this information, let me proceed with the calculating how to calculate the carrier concentrations in the case of intrinsic semiconductors. Okay, right. So let me proceed with the intrinsic semiconductor. In intrinsic semiconductor, how to calculate carrier concentration, right? Before going to see that, let me just introduce this. See, I have told you in the EK diagram, let me consider direct band gap semiconductors. So this is the conduction band and this is the valence band. So in conduction band, there are many energy levels are available which are very closely spaced. Okay, so in conduction band we have many energy levels. Similarly, in valence band also we have many energy levels. Each level can accommodate maximum of 2 electrons. Okay, now this is the top of the valence band. The energy, this is energy axis and this is K axis. Okay, this is the top of the valence band. The energy correspond to this is represented as EV. Okay, valence band energy or top of the valence band energy, and this energy correspond to bottom of the conduction band. Okay, and I have told you this gap is what we call as band gap. Okay, now at temperature of 0 Kelvin, at T equal to 0 Kelvin. Very, very important. At T equal to 0 Kelvin, right, at T equal to 0 Kelvin, valence band is fully filled and conduction band is fully empty. Okay, valence band is fully filled, conduction band is completely empty, right? Conduction band is empty, right? So there are no carriers available or free carriers available, right, to make the to show conductivity, okay, or to show conductions, right? Therefore, at 0 Kelvin, semiconductors, right? See, what I'm trying to say is, in valence band is fully filled. That means there is no mobile carriers available here. Similarly, in conduction band is fully empty, so there are no carriers available. Therefore, at 0 Kelvin, semiconductors do not show any conduction, or semiconductors actually behave like insulators. Semiconductors actually behave like insulators at 0 Kelvin. As temperature increases, what will happen? Okay, let me write here. At temperature above 0 Kelvin, say for example room temperature. At room temperature, see, the band gap, okay, the band gap is small, whereas the thermal energy available, right? If the average thermal energy available, right, at temperature T, if it is greater than the band gap, right? If thermal energy available, average thermal energy available, if it is greater than band gap of the material, what will happen? Electrons, right, undergoes transition from valence band to conduction band. Electrons undergo transition from valence band to conduction band, right? So now what will happen? Let me show this in a band shape. Instead of showing this EK diagram, let me draw like this. This is how we draw in lower classes, okay? Energy axis. So now what I'm going to show is that, so this is the valence band and this is the conduction band. Now, due to thermal excitation, due to thermal energy that is available, okay, and it is sufficiently available, therefore the electrons present in the valence band undergo transition, right, undergo transition from valence band to conduction band. When one electron makes transition from valence band to conduction band, okay, it will create a hole in the valence band and you will get an electron in the conduction band. Okay, you will get a hole and you will get an electron. You will get a hole and you will get an electron. So for each transition, okay, you will get an electron in conduction band and a hole in valence band, right? This is purely due to thermal excitation, right? So at temperature above 0 Kelvin, thermal excitation takes place. It is purely thermal excitation. Due to thermal excitation, you will get electrons in conduction band and you will get valence in holes in valence band. Holes mean positively charged. Okay, positive charge. Now keep this in mind. Electrons in conduction band, okay, will show conduction. It will conduct current. Similarly, holes in valence band also show conduction. So for semiconductor to conduct current, okay, you require either electron in conduction band or holes in valence band. Okay, so in the case of intrinsic semiconductor, right, every thermal excitation, right, or for every transition, you will get a hole in the valence band and electron in the conduction band. Therefore, in intrinsic semiconductor, right, the semiconductor conduct current or the conduction takes place both by electron and holes. Okay, so here these electrons in conduction band and holes in valence band are called carriers, right? They carry same charge with opposite sign and masses are different. Okay, the masses are not same, they are different. Okay, right. So, and here since the excitation takes place only due to thermal energy, number of holes in the valence band and number of electrons in the conduction band are equal. Okay, or I can say in the other way, concentration of electrons. Let me represent this as N. N means concentration of electrons in conduction band. P means concentration of holes in valence band. Why I am saying concentration? Concentration means number of electrons per unit volume. Here P means number of holes per unit volume. N means number of electrons per unit volume. P means number of holes per unit volume. Since these electrons in conduction band and holes and valence band are created only due to thermal excitation, right? The number of electron in the conduction band and number of holes in the valence band are equal in the case of intrinsic semiconductor, right? So in the case of intrinsic semiconductor, N is equal to P, right? So keep this in mind. This is very, very important. This is for intrinsic semiconductor. Okay, then the next important point that I like to discuss here is that what about the mass of electron in conduction band and mass of hole in valence band? Okay, are the masses are exactly equal to the rest mass of electron? You know very well, rest mass of electron is 9.1 into 10 to the power minus 31 kg. Okay, is the electron present in conduction band has same mass? No. The mass of the carriers present in carriers means electrons in conduction band and holes in valence band. These charge carriers are the carriers present in semiconductors. They do not have, okay, often they do not, they have different mass value compared to the rest mass. Okay, so you know very well, energy is equal to h bar square k square by 2m. Okay, this is the relation between E and K. Okay, you'll get a parabolic relation. Right, now let me differentiate this E with respect to K. dE by dK equal to, I'll keep this h bar square by 2m as such, and K square on differentiation you'll get 2K. So this two cancels. I'll differentiate this again, d square E by dK square. Okay, I'm taking second order differentiation. What I'll get is h bar square by m, okay, and K on differentiation become 1, right? And this mass, okay, I'll bring this mass this side, m is equal to h bar square over d square E by dK square. Yeah, see, this is very, very important. Now mass of electron or the mass of the charge carrier depends on the second derivative of this value. The second derivative value, okay, second derivative of this, okay, the magnitude of this depends on the curvature. It depends on curvature. Okay, you know very well, for straight line curvature, there is no curvature. So for straight line, second order differentiation value is 0. As the line bends like this and form a curve, what will happen? Curvature increases. Right? So for this, second order differentiation value is 0. As the curvature increases, second order differentiation value also increases. Okay, so in the case of EK, see, in the case of in EK diagram, you might have seen this. In EK diagram, see, suppose this is the conduction band, and let us say this is valence band. Right? Purposefully I have drawn like this. See, conduction band has large curvature. whereas valence band, right, has a small curvature. If the curvature is large, second derivative value is large. If second derivative value is large, mass will be less. Okay, and I'm going to represent this mass with the symbol m star, where m star is called the effective mass. So effective mass of charge carrier depends on the curvature of the this EK diagram. Okay, so in most materials, okay, curvature of conduction band and curvature of valence band are not equal in most semiconductors. Therefore, the effective mass of electron in conduction band, okay, and the effective mass of hole in valence band, right, they need not be same. Okay, so keep this in mind, where m star E represent effective mass of electron, right, in conduction band, and I'll represent m star H, which is effective mass of hole in valence band. Okay, if you go from material to material, when you move from one material to another material, the curvature changes. Therefore, the effective mass of electron in conduction band in one material and the effective mass of electron in conduction band in the other material, they need not be same. They vary because the curvature changes. Okay, so keep this in mind. See here, curvature increases, right? As the curvature increases, the second derivative value will increase. If second derivative value increases, what will happen? The effective mass will decrease. Therefore in here we have large curvature, therefore effective mass is less. Here the curvature is small, so effective mass is large. Okay, so keep this in mind. This is very, very important. Right, this is regarding the effective mass of charge carriers in conduction band and hole in valence band. Right, then now let me discuss about the how to calculate the value of N and P in the case of intrinsic semiconductors. Okay, yeah. See, to calculate N, what is N? N is nothing but concentration of electron in conduction band. Okay, what we have to do is that we need to find out the density of states in the conduction band. Okay, so in the conduction band, as I have told you, there are so many levels, there are so many energy levels are there, they are very closely spaced. What we need to do, we need to identify what is the density of states. Then it is not that all the states are occupied, right? You know very well, because due to thermal excitation only the electrons move to conduction band. Therefore, the number of electrons, right, that is actually occupying the energy levels are less. Therefore, we need to identify how many levels are actually occupied. So what I'm going to do to calculate this value of N, right, I'm going to make an integration. What is the integration? What is the density of state in the conduction band, density of energy states in the conduction band, into how many states are, what is the probability of occupying a state? This is probability of occupancy of state. This you can get from Fermi-Dirac statistics. Fermi-Dirac statistics or distribution statistics. You can get this from Fermi-Dirac statistics. Okay, and into D. This integral will give you the number of electrons, right, in the conduction band, or concentration of electron in the conduction band. This is actually density of states. What is density of state? Number of energy states available per unit volume per unit energy interval. Okay, and we know the value of this density of state in the conduction band. Let me give the value directly. Density of states in the conduction band is equal to 1 by 2 pi square into 2 into effective mass of electron in the conduction band over h bar square whole power 3 by 2 into E minus EC whole power half. Okay, this energy, that is the bottom energy corresponds to EC, right? You take whatever energy above that, okay, that is E minus EC whole power half. So we will get what is called the density of states in the conduction band. E minus EC will give me, we are taking only these levels, right, the energy levels present in the conduction band, right? Similarly for valence band, let me write here itself. In the case of valence band, what is the density of state in valence band, which is equal to, same expression I'm going to use, 1 by 2 pi square into 2 into, instead of effective mass of electron, I'll put effective mass of hole, divided by h bar square whole power 3 by 2 into, now for valence band, this is the EV energy, and we should take energy levels below that. Therefore EV minus E whole power half. This will give you the density of states in the valence band. Okay, now what I'm going to do, I'll substitute this here. Okay, so we'll see how to find this value. N is equal to density of state in the conduction band, which is integral. Okay, actually this band ends to in the last class I have told you, this value, the top of this band value is EC plus chi, where chi is the electron affinity, right? Above that there is no band, or there is no energy levels available, or there is no electrons occupying those positions. Therefore even if you make the integration from EC to EC is the lowest value of energy, even if you go from, instead of EC plus chi, okay, let me write once, we have to integrate up to this, and GC value is 1 by 2 pi square times 2 into effective mass of electron by h bar square whole power 3 by 2 into E minus EC whole power half. Okay, this is the density of states in conduction band, into Fermi-Dirac distribution or function, which is nothing but 1 by 1 plus E power Fermi energy EF minus EI, or I'm sorry, E minus EF, this is EI, or simply E minus EF by KBT, So this is the Fermi-Dirac function into DE energy. Okay, now what I'm trying to say is that even if I integrate, right, from instead of EC plus chi, even if you put infinity, nothing going to wrong, nothing going to make any difference, because only up to certain states are occupied, right? Above that all the states are empty. Automatically this Fermi function becomes 0. So above, if you suppose, if at all all the levels are occupied, right, in conduction band, right, then up to EC plus chi the values are occupied. Above that automatically the Fermi function becomes 0. Therefore instead of EC plus chi, even I can put infinity. So EC up to infinity, right, and I'll keep all these terms as such. Now in this 1 by 2 pi square, this value, these are all constants, so I can take it out. Let me write to the next page. I'll take it out. So N is equal to 1 by 2 pi square into 2 into effective mass of electron over h bar square whole power 3 by 2. Okay, these are all constant quantities, so I'll keep them out. Integral EC power infinity, and inside we have E minus EC whole power half divided by 1 plus e power E minus EF, where EF is the Fermi energy, by kBT, right, into dE. This is EF is the Fermi energy of the semiconductor. Okay, what is Fermi energy of a semiconductor? Yes, we'll see. Right, in metals, you know very well, in metals Fermi energy is the highest occupied level, but in semiconductor Fermi energy is different. What is meant by that? Yes, we'll discuss. Now for this integration, right, it is actually how to evaluate this integral, right? For this purpose, what I'm going to do, direct evaluation of this integral is difficult, so what I'm going to do, let me introduce some terms. Okay, I'll define some terms, like say I'll introduce a term eta, where eta is equal to E minus EC by kBT. I'll just define a term like this, E minus EC by kBT. This is eta. Similarly, I'll introduce another term, eta C. What is eta C? Eta C is equal to EF minus EC by kBT. I'm just defining two terms like this, eta and eta C. Right? Now, what is d eta? D eta equal to EC is constant for a given material, kBT everything is constant. So if I differentiate this, I'll get 1 here, so I'll get 1 by kBT into dE. 1 by kBT into dE. So this is d eta. Right? Then I'll calculate one more quantity. What is eta minus eta C? This minus this. If I subtract this, EC cancels, so you'll get E minus EF. You'll get E minus EF over kBT. Okay, I'm just defining some terms like this. Now I'm going to incorporate these values here. Okay, so I'll get N is equal to 1 over 2 pi square into 2 into effective mass of electron by h bar square whole power 3 by 2 into integral EC. Okay, now we have to since we have changing the energy into a new function eta, so we have to change the limits. Okay, now when energy is EC, what's the value of eta? If E is in the place of E, I'll put EC. EC minus EC is 0, therefore eta becomes 0. Okay, when energy is EC, eta value is 0. Then when it is infinity, when energy is infinity, yes, eta also infinity, so the integral now becomes 0 to infinity. Okay, then what is E minus EC? So from this I can write E minus EC is eta by eta into kBT, and we have whole power half, therefore I can write kBT power half. Let me write here. Okay, so see what I'm trying to say. Okay, let me write once. So E minus EC is eta into kBT, whole power half is there, therefore kBT power half and eta power half. Okay, divided by 1 plus E power E minus EF by kBT. E minus EF by kBT is eta minus eta C. Okay, so I'll keep them as such, into what is dE? From this, dE is equal to kBT into d theta. So kBT into d eta. Right? Now I'll kBT power half is there, kBT power 1 is there, so it will become kBT power 3 by 2. I'll take this kBT power 3 by 2 out, so I can write this as 1 by 2 pi square into I'll bring this term inside, so I can write this as 2 into effective mass of electron. What is h bar? H bar is nothing but h by 2 pi. H bar square is h square by 4 pi square. So I'll put h square here, h square, and bring the 4 pi square in the numerator. 4 pi square. and this become kBt power 3 by 2. I'll bring everything inside kBt whole power 3 by 2, right? And what's left with 0 to infinity eta power half by 1 plus e power eta minus eta c into d eta, right? Here we'll get some form of integral, and this integral is very famous. This integral is called Fermi-Hoff integral. This integral is called Fermi-Hoff integral. Fermi-Hoff integral. And how to evaluate the Fermi-Hoff integral? Yes, there are methods available. You can even use an Excel sheet and you can calculate. Okay, so you can calculate this, and in many books these values are available for different values of eta. So you can take depending upon your material, right? You can calculate eta, and you can find this integral. Okay, and this integral is very famous. It's called Fermi-Hoff integral. Okay, and it is represented as, let me write in the next page. How to represent this? Let me write in the next page. So what we had left is 1 by 2 pi square into 2 into effective mass of electron into 4 pi square into kBt by h square whole power 3 by 2 into the Fermi-Hoff integral. I am going to represent that Fermi-Hoff integral like this. Okay, f 1 by 2 eta c. It is called Fermi-Hoff integral. Okay, this is how we represent Fermi-Hoff integral. So this symbol indicates Fermi-Hoff integral. Now what I'm going to do, I'll multiply the numerator and denominator. I'll make a small manipulation here. Root pi by 2. I'll multiply this by root pi by 2 and 2 by root pi. Okay, if I do like that, nothing going to change, right? Now what will happen? This will simplify to a quantity that is 2 into 2 pi m kBt by h square whole power 3 by 2 into 2 by root pi of the Fermi-Hoff integral with value eta c. Okay, and this is a constant for a given material, for a given semiconductor, and I am going to take this constant as Nc. Nc is a constant for a given material at a given temperature. Okay, so concentration of electron in the conduction band is given as Nc into 2 by root pi, right, into the Fermi-Hoff integral. Fermi-Hoff integral f. This is a way of representing f here. It's called Fermi-Hoff integral eta c. Okay, so if you know the value of Fermi-Hoff integral, yes, you can calculate the concentration. Now if I plot, see, if I plot 2 by root pi into the Fermi-Hoff integral values, right, versus energy E. Okay, I'll get let me draw a curve like this, and this curve represent the function, the plot of e power eta. If I plot e power eta, I'll get this, and I'll get a function, right, which appears like this. So if I plot this value versus e, I'll get a quantity. It goes like this, like this, like this, right? So this is actually the 2 by root pi and the Fermi-Hoff integral f of eta c. See, this curve is the e power eta curve, and this is the actual curve that we have plotted. Now what is that you have to keep in mind here is that, see, the actual curve is this. So if you want to calculate the concentration of electron in conduction band, right, at various energy, higher energy levels, right? At higher energy levels, yes, you have to use only this. But what I'm trying to say, up to this, see here, up to this, e power eta value and this value, value are almost same. Above that it changes. Therefore, if the energy is lower, okay, to certain value, if energy is lower to certain value, then this quantity and e power eta are one and the same. See, what I'm trying to say is that suppose if eta c is sufficiently low, right? If eta c is very low, right? Is sufficiently low, then the concentration N, right, in conduction band becomes equal to Nc into, instead of that integral, okay, 2 by root pi Fermi-Hoff integral, I can put e power eta. What is eta? Eta is EF minus EC, correct? Eta is nothing but, I'm sorry, eta c. Yeah, eta become eta c because we are calculating eta c. So EF minus EC by kBt, right? So now see the function, this N, right, or this equation, right, is something look like Boltzmann distribution. Something looks like Boltzmann distribution. Okay, when this will occur, listen, you know very well eta, see, I'll write here, what is eta c, or what is eta? Eta is equal to E minus EC by kBt, okay? When we have to use this, you know very well eta is equal to E minus EC by kBt. Suppose if E what is eta c? Let me write here. What is eta c? Eta c is equal to EF Fermi energy minus EC by kBt. Okay. Okay. If this gap is very large, okay. If this what I'm trying to say, if EC is very high, right, compared to EF. If EC is very high compared to EF, then this value will be negative, right? Okay, or we can say in the other way also. See, what I'm trying to say is that if eta c is sufficiently low, means suppose assume that eta c is less than some value, say I'll take some value here. Suppose this is say minus 3. Suppose minus 3. If eta c value is below minus 3, then you can use this expression. Why? Because what is eta c? Eta c is nothing but EF. What is the meaning for this? EF minus EC by kBt is less than minus 3, or EF minus EC is less than minus 3 kBt, or we can say EC minus EF is greater than 3 kBt. What's the meaning? The meaning is that EC minus EF. Yeah. See, in semiconductors, so this is the conduction band and this is the valence band, right? The Fermi energy usually appear between the conduction band and valence band. Okay, suppose assume that this is the Fermi energy EF and this is EC. If this gap is large, that is EC minus EF, if it is greater than 3 times kBt, see, I have taken this minus 3 just like that, but depending upon the material, this value will change. Okay, just for understanding purpose, I have taken this value. If EC minus EF is sufficiently greater, that means if this gap is large, okay, then this Fermi integral, right, instead of Fermi integral, you can use the Boltzmann distribution. Okay, so this equation is can be used if the gap between EC and EF is sufficiently large. Okay, so that's the point you should keep in mind. Similarly, you can find the concentration of holes in the valence band. using similar type of expression, but instead of NC you'll get what is called NP. NP into e power, instead of EF minus EC I'll get EV minus EF by kBT. So this is the concentration of holes, right, in the valence band. Here again the condition is if this gap should be large. Okay, so whenever Fermi energy is present approximately at the middle of conduction band and valence band, yes, you can use the Boltzmann approximation. This is called the Boltzmann approximation, right? Boltzmann approximation. Otherwise, suppose if EF Fermi energy is very close to EZ or Fermi energy is very close to valence band, then there is no other go. We have to use we have to calculate the Fermi off integral, and from that you have to calculate the value of n. Okay, if the Fermi energy is present approximately at the middle or approximately in between the valence band or EC and EV, yes, then you can use this Boltzmann approximation. Okay, yeah. So what I'm trying to say here is, under Boltzmann approximation, right, the concentration of electrons in the conduction band can be given as NC into e power EC minus, Fermi energy EF minus EC by kBT, and concentration of holes, right, in the valence band can be given as let me write here, concentration of holes is equal to NV, we can use, that's the correct word, I'm sorry. So here I make a small correction, this is not NP, this is NV, standard notation. NC is constant, NC is a constant corresponding to conduction band. NV is the constant corresponding to valence band for a given material, right? So NV is a constant for a given material into e power EV minus EF by kBT. We'll get an expression like this. So this is under Boltzmann approximation. What is Boltzmann approximation? Remember, if the gap between EC and EF is large. Similarly, if the gap between EF and EV is large. Okay, or I can say simply, if the Fermi energy is present approximately at the middle between EC and EV, then you can use this expression to calculate the concentrations. Right? Now what I'm trying to say is that, see, in the case of intrinsic semiconductor, okay, the value of N and P are equal. Okay, right? In the case of intrinsic semiconductor, N value and P values are equal, which will represent as simply Ni. What is Ni? Ni is the intrinsic concentration of the carrier. Okay, so suppose if I multiply N and P, what will I get? How to get the value of Ni? I'll multiply this N and P. If I multiply N and P, you have to multiply NC into NV, and you have to multiply these two. So e power of this into e power of this. So you have to add the power. If you add the power, EF get cancelled. So you will get what is called, you'll get an expression like this: e power minus EC minus EV by kBT. You'll get an expression like this. What is EC minus EV? EC minus EV is nothing but band gap. So N into P equal to NC into NV into e power minus band gap of the material EG by kBT. Okay, and you know very well N and P both are equal, which is equal to Ni. So if we put in the place of N and P, I'll put Ni. So I'll get Ni square. Ni into Ni is Ni square. Ni square is NC into NV into e power minus EG by kBT. And what is Ni? Intrinsic concentration is equal to square root of NC into NV into you have to take square root of this, which is nothing but e power minus Eg by 2 kBt. So this is the expression for the intrinsic concentration of the intrinsic semiconductor. If you want to calculate the intrinsic concentration for a semiconductor, okay, you must know the, I'm sorry, I keep doing this mistake, I'm sorry. So to find the intrinsic concentration, you have to calculate Nc and Nv for the given material, and it is a constant. Nc and Nv values are constant for a given material at a given temperature, right? And into e power minus Eg by 2 kBt, right? This is the expression for intrinsic concentration. Okay, so you can calculate the intrinsic concentration using this expression. Now let me take a logarithm of this. Okay, if you take logarithm, I'll get ln Ni equal to ln of this constant Nc into Nv, and if I take logarithm, I'll get minus Eg by 2 kBt. Okay, so if I plot ln Ni versus 1 by t, if I plot ln Ni versus 1 by t, we'll get a straight line with a negative slope. We'll get a straight line with a negative slope. Okay, the slope of this straight line is nothing but minus Eg by 2 into kb. So if you know the slope, you can calculate the band gap, right? This is very, very important, so keep this in mind. Now so I have introduced the way to calculate the value of Ni, okay, under Boltzmann approximation. This is under Boltzmann approximation, right? Intrinsic concentration equal to square root of Nc into Nv into e power minus Eg by 2 kBt, right? Then the next one, which is very, very important, how to calculate the Fermi energy. How to calculate the Fermi energy, right? So how to calculate the Fermi energy for the intrinsic semiconductor. So I'll put EFI. EFI means Fermi energy for intrinsic semiconductor. Yeah, we know very well N is equal to P for intrinsic semiconductor. What is N? N is nothing but Nc into e power minus I'm sorry, instead of minus I'll put e power EF minus E by kBt, and P is equal to Nv into e power E minus EF, okay, by kBt. Sorry, this is EF minus EC, and this is EV minus EF by kBt, right? So if you make if you equate these two, I'll get this expression. Now what I'm going to do, how to calculate the intrinsic Fermi energy. Yes, how to do that. Now I'll bring this Nc to this side, okay, and I'll bring this one to the left hand side. See, what I'm going to do is that I'll keep this one as e power EF minus EC by kBt, and I'll bring this term to the left hand side, so it'll come to the denominator. If I bring it to the numerator, I'll get e power minus EV minus Fermi energy by kBt equal to Nv by Nc. Okay, so if I multiply, you have to add the power. So here I will get minus EV, here I will get plus EF. So what will I get is e power 2 EF. Let me do it directly. E power 2 EF by kBt into e power, this is e power minus EC, here you have minus EV, so I'll take minus is common, so I can write minus EC minus EV by kBt. Okay, EC minus EV by kBt. Now we'll make some rearrangement here, Nv by Nc. We'll make some rearrangement. So I'll bring this to the right hand side, so it will go to the denominator, then Okay, I've taken minus common, no? Yeah, so this become plus, right? So if you bring it to the right hand side, it will come to the denominator, and if you bring it to the numerator, it will become positive. So e power 2EF by kBt can be written as NV by NC into e power EC plus EV by kBt. Okay, now I'll take logarithm both sides. So if I take logarithm, I'll get 2 into EF by kBt equal to ln NV by NC, and here if I take logarithm, I'll get EC plus EV over kBt. Okay, now I'm going to multiply throughout by kBt, and I'm going to divide by 2. So if I do like that, what will I get? Let me write to the next page. See what I'm going to do is that to calculate the Fermi energy, right, I'm going to proceed like this. So 2 into EF, I'll multiply everything by kBt. So I'll get kBt into ln NV by NC plus, if I multiply by kBt cancel, so I'll get EC plus EV. Right, now I'll divide throughout by 2. So Fermi energy equal to 1 by 2 into kBt ln NV by NC, and here I'll get EC plus EV by 2. Okay, now I'll make some more simplification here. Yeah, what I'm going to do, I'll subtract both sides by EV. So if I do so, I'll get EF minus EV equal to, yeah, I'll get 1 by 2 times kBt ln NV by NC plus, here I'll get if I subtract by minus EV, I'll get EC minus EV by 2. I'm subtracting both sides by EV. So if I subtract this by EV, okay, I'll get EV by half minus EV, which is minus EV by half. EC minus EV is EG. Therefore, I can write this as EV minus EF, or EV equal to, I'll bring this EV to the EF, EF equal to EV plus EC minus EV is EG by 2 plus 1 by 2 into kBt ln NV by NC. Right? Yes, this is the expression for Fermi energy, and this is for intrinsic semiconductor. So I'll put EFI. EFI is the intrinsic Fermi energy for the intrinsic semiconductor. What does this tell you? Above EV, at what value EF will exist? Above EV. Okay, so this is this will give you, right, above EV, at what value the Fermi energy will exist. Okay, yes, you can calculate using this formula, right? And you know very well, NV by NC. What is NV and what is NC? NV is nothing but 2 into 2 pi m star h kBt effective mass of hole by h square whole power 3 by 2. And what is NC? NC is 2 into 2 pi effective mass of electron into kBt by h square whole power 3 by 2. Then what is NV by NC? NV by NC is nothing but, if I divide these two, except the effective mass of hole and the electron, remaining things cancels. So I'll get effective mass of hole by effective mass of electron whole power 3 by 2. Okay, now in the place of NV by NC, if I substitute this here, so I'll get whole power m star h by m star e whole power 3 by 2. 3 by 2 will come to the come in front, so I'll get 3 by 4 here. Therefore, we have alternative expression for this, for Fermi energy. So what is the Fermi energy above, at what value the Fermi energy will exist above above the EV value. So EFI equal to EV plus the band gap EG by 2 plus, now if I put this value here, I'll get 3 by 4 times kBT ln effective mass of hole by effective mass of electron. Okay, yes, this is an alternative expression for the Fermi energy, and this can be used to calculate the Fermi energy of an intrinsic semiconductor. Okay, so we have discussed, right, how to calculate the intrinsic concentration, and we have also discussed how to calculate the intrinsic Fermi energy for a material. Okay, yeah, I stop here. We'll continue the semiconductor materials, right, and other properties in the next class. Okay, thank you for listening.